Hi everyone. This lesson is our first in our unit on waves, and our goal here is to just learn about what a wave is, the different types of waves, and some of the different characteristics that define and differentiate waves from each other. So there's going to be a lot of new terminology in this lesson, probably more here than in the rest of the unit combined. So I know it's going to be a term-heavy lesson here. Bear with me, you can do this, I believe in you. Okay, so we're going to start off with just like what a wave is. Now, if you did the investigation last time, you had a chance to watch this video of the wave being done through a stadium. And I asked you, like, what was moving through the stadium here? Like, what is this wave? And so what I hope you notice is that what's actually moving is not people exactly. Like, yes, there are people moving up and down, but as we see the wave moving from right to left here, it's not like there's one person that's moving like from seat to seat all the way around. What's really moving along with that wave is energy. That one person jumps up, moves, has energy, and then the energy gets passed on to the next person, and so then they jump up, and then the next person, and the next person, and so on and so forth. When we see a wave moving, what we're seeing is the movement of energy, not individual particles moving with the wave, but energy passing from particle to particle to particle as it goes. Now, whatever material is carrying that energy, whatever material the wave is passing through, we call that the medium. And so for this particular wave that we just saw here, the medium was the fans in the stadium. They were the objects that were carrying that energy across the stadium there. And if all the fans were gone, then there would be no wave because there's no one to pass energy along. Okay, now this idea of a medium ends up being really important for characterizing and classifying different waves. So we've got mechanical waves and non-mechanical waves. Mechanical waves absolutely need a medium in order to travel. In the absence of particles to carry the energy, those waves cease to exist. Now the main one we're going to focus on in this unit is sound waves. Sound waves are mechanical waves. The way that you're able to hear me right now is because the speakers from your computer or phone or whatever you're watching this on ultimately are vibrating the air right next to the speaker, which causes those air particles to like bump into the air particles near them and keep bumping into the air particles up, up, up until eventually those vibrations reach the air particles that are right by your eardrum, and then your eardrum vibrates and a whole bunch of stuff happens and transduction and all these good things to cause you to hear and perceive that sound. But sound waves have to be carried by particles that are vibrating. Seismic waves, so the movement of tectonic plates, earthquakes, those would be examples of mechanical waves where the medium is the earth, and then water waves obviously are mechanical waves where water is the material that the wave is traveling through. So those are our mechanical waves, but then there are also non-mechanical waves. And non-mechanical waves can travel through a medium, or they can travel through not a medium. They can travel through a vacuum where there are no particles, there's no matter, but the wave is still able to propagate through nothingness. What type of wave do you think is capable of moving through a vacuum? Well, fortunately for us, the vacuum of space does still allow light waves to travel through. Now, light waves are also known as electromagnetic waves because technically they're just these oscillating electrical and magnetic fields, which we'll not get a ton into here, but just a little bit there. So light waves are capable of traveling through a medium. So light can go through water, through air, but it can also go through the vacuum of space, which is good because otherwise Earth would be a very sad, dark, cold, dead place. So yay for light being a non-mechanical wave. All right. Another way that we can be classifying different types of waves has to do with sort of the mechanism by which they are passing energy along. And so to illustrate that, we are going to send a wave across a slinky. Now again, a wave is just energy. So the question here is, what are the different ways that I can send energy from the right side of the slinky over to the left side of the slinky? Now, sort of the classic way that people tend to think about is something like this, where you get a nice little like sine wave, you move it up and down. But you can also pass energy down the slinky by moving the slinky back and forth as well. So we see these two different ways that energy, that waves can propagate across the slinky. And this brings us to our two major types of waves here. Transverse waves are waves in which our particles are going to be oscillating perpendicular to the direction that the wave propagates. That was the first type of wave that we saw in the slinky, where the wave was moving horizontally, but I was moving the slinky vertically. So I was swinging the slinky vertically, and then that energy moved across horizontally. And we can see that in the animation here as well. Our blue dot is moving up and down, but we see the wave moving left to right, right? So those are transverse waves, where wave movement is perpendicular to particle movement. And our other option is longitudinal waves. Now in longitudinal waves, our particles are oscillating parallel to the direction that the wave is moving. That was the second type of wave we saw in the slinky video just now, where the wave was moving horizontally across the slinky, and I was moving my hand horizontally as well, moving the slinky and sending that energy down. Right. And we can see that here in this animation as well, that we see this wave that's propagating along here as the particles are kind of bobbing back and forth horizontally. All right, now a little bit more about each of those types of waves. So transverse waves, again, are those nice, like, classic sine waves. Light waves fall into this category. Light waves are transverse waves. Some seismic waves are also transverse as well. And if we look at some of the defining features of this wave, we see places where we sort of reach a high point, we call that a crest or a peak, and then the lowest point, which we call the trough. So with transverse waves, we have these alternating crest, peak, or crest or peak, trough, crest, trough, and so on and so forth. Now, with longitudinal waves, we don't have that clear sine wave. We don't see the up and down movement there. So things look a little bit different there. Now, a key thing to note is that sound waves are an example of longitudinal waves. So the particles are just vibrating back and forth and moving along that way. Some other seismic waves also fall into this camp as well. Now, we don't have peaks and troughs or crests and troughs for longitudinal waves. Instead, what we see is there are places where the particles kind of end up moving towards each other. They're all kind of bunched together, and then places where they're farther apart again. So we kind of get this like accordion movement of particles along here. And so places where our particles are really close together, we call those compressions. And then places where the particles are farther apart, we call rarefactions, all right, because it's a lower density area. It's rarefied, essentially. And so instead of having these alternating peaks and troughs in longitudinal waves, we have alternating compressions and rarefactions. But ultimately, the general cyclical nature of waves is the same for both of those. And just to kind of illustrate that for you, sorry for the horrible resolution as I tried to zoom way in on this picture, but we can see overlaid on each other a transverse wave in green, and then sort of a longitudinal wave in a slinky in this sort of teal color. And we can see that compressions really are kind of analogous to peaks, and rarefactions are kind of analogous to troughs. So either way, we've got this cyclical alternating nature for both of those types of waves, whether transverse or longitudinal. Now, let's focus in on the transverse wave for a little bit, just because since it's in 2 dimensions, it's a little bit easier for us to kind of pick apart different pieces of it. So looking at this transverse wave, this sine wave that's in that sort of lime green color here, there are a couple different sort of parameters or dimensions that we can use to think about the shape of that wave in space. One is the amplitude, which we see here, we can kind of think of as like the height of the wave, and we're going to give that a better definition in just a moment. But amplitude, we see sort of like the height of the wave, how much the particles are moving up and down there. But then across the other dimension, we also want to keep track of the wavelength, all right, the length of the wave, how far apart these different troughs are, or rarefactions, or peaks, or compressions, depending on how we want to measure and what type of wave we're dealing with. So with that distinction in our mind then, let's jump over to a little bit of wave anatomy and some of the ways that we can characterize these waves that we are dealing with numerically, because I know you've missed numbers these last few weeks, right? So first thing is amplitude. So again, that was sort of like the height of our wave for the transverse wave. A more precise description, though, of amplitude is that it describes how much our particles are being displaced from their rest position. So basically, how far out of their normal position are our particles being jostled because the wave is moving through? Is the wave pushing them like way over, or is the wave just like disturbing them a teeny tiny bit? Now, given that amplitude is really just a measure of particle displacement, what units do you think we use to measure amplitude? We're going way, way back to September, to August even, with this one. But displacement, we measure in meters. And so we can measure amplitude in meters as well, or centimeters, or millimeters, or nanometers, or whatever is appropriate for the situation. But meters is sort of our good default unit for this. Now, wavelength also describes a distance, also measured in meters, but instead of looking at the displacement of an individual particle that's being disturbed by the wave, the wavelength describes how far the wave travels during the course of a single cycle. Now, an easier way for us to kind of visualize that is to choose two adjacent points on the wave that are the same. So essentially like two adjacent peaks or two adjacent troughs or two adjacent compressions, and just see how far apart are those two. And that tells us what the wavelength is. How far does the wave travel? How long is one complete cycle of that wave? Okay. Now, a couple other parameters of waves to be familiar with that are not like directly like spatially measurable, but that are still important to know. One is period, all right? And period describes the time that it takes for our wave to complete one cycle. How long does it take to go from one peak to the next peak, or from one rarefaction to the next rarefaction, all right? Now, given that period measures time, what do you think it's measured in? Seconds. Could be other things as well, but seconds are our default unit. And then last parameter for us to consider is frequency, which measures something similar to period, but in a slightly different way. Frequency is describing for us how many cycles are completed per second for our wave. And it's measured in hertz, and hertz is just a fancy way of saying cycles per second. Okay, so just to contextualize this a little bit, typical hummingbird, as it's flying around, will flap its wings 50 times per second. So we would say that that hummingbird is flapping its wings at a frequency of 50 hertz, because it's completing 50 full cycles. It's flapping its wings 50 times every second, so that's 50 hertz. Okay. Now, it turns out that we have evolved in such a way that we're really good at picking up on some of these parameters of waves without even like having to directly measure. Like, we just are like attuned to some of those differences. So let's talk about that a little bit before we wrap this up. So sound waves, we are able to discern the amplitude of a sound wave, whether it is a high amplitude sound wave or a low amplitude sound wave. How do you think we are able to discern that difference? Well, our layman's term for sound wave amplitude is volume. So a high amplitude sound wave, a sound wave where particles are getting really greatly displaced by that wave passing through, we hear that as a loud sound. And a low amplitude sound wave sounds quiet to us, right? Now, jumping over to light, how do you think we perceive the amplitude of a light wave? So pretty similar to the idea with sound then, since high amplitude sound waves are loud, high amplitude light waves are bright. Okay, so we're talking about like the intensity, the amount that we're picking up on here. So high amplitude light waves are bright, low amplitude light waves seem dim to us. All right, so that's amplitude. Let's jump over to how we perceive frequency, the number of cycles per second for our wave. So for a sound wave, how do you think we're able to perceive the difference between a high frequency sound wave and a low frequency sound wave? Frequency we pick up on as pitch. So a high frequency sound wave sounds high pitched to us, and a low frequency sound wave sounds low pitched to us, right? And then lastly, how do you think we are able to discern frequency for light waves? Well, beyond the brightness of the light wave, the other main thing that we're able to pick up on is color. So in the visible range for light, higher frequency light waves will appear bluer and lower frequency light waves will appear redder. So it kind of follows this spectrum. So the lowest frequency that we're able to see, it looks red to us, and as we increase the frequency, it looks orange and then yellow and then green and then blue and then purple, and then we can't see it anymore. All right. So frequency we perceive in the form of color in terms of light waves. All right. Now I specified for light that that we see frequency as color only in the visible range. Let me elaborate on that just a little bit here. Okay. So it turns out that what we refer to as light in sort of an everyday layman's perspective is just a really tiny subset of what physicists refer to as light. So this brings us to the idea of the electromagnetic spectrum, because light, again, is just electromagnetic waves, all right? So there is a very small range of electromagnetic waves that you and I are capable of seeing, that we have evolved to be able to perceive with our eyes. But it turns out that if we change up the frequency outside of that range, there's a whole bunch of other types of waves that you're familiar with, but you maybe didn't know were like the siblings of light. Okay, so radio waves describe the absolute lowest frequency light waves, and then as we increase that frequency, we get up to microwaves, like, yes, the microwaves in your microwave that make food hot, you know, all of that. And then up into infrared. If we continue increasing the frequency, that's where we get to the visible range. And so there's this little narrow band of frequencies that we can see. And then if we keep increasing the frequency, we get up to ultraviolet or UV rays, and then X-rays, and eventually gamma rays, which hopefully we're not encountering too often because, you know, bad things, cancer, all of that good stuff. Okay, so it turns out then that all of those different types of waves are really the same as light waves, just at different frequencies that you and I have not evolved to be able to see, which is kind of weird to think about. It turns out there are other animals that can see electromagnetic waves outside of what we consider the visible range. So like reindeer, for example, are able to see up into the low ultraviolet range. So like UV light, like we can't see at all, but reindeer could see it like it's a color. Like they can see it. And there are various other animals that can kind of pick up on UV or infrared ranges. And it's just kind of weird to think about, like, if we could evolve and change over time and eventually develop photoreceptors to pick up on like radio waves, we would just be like bombarded with all of these radio waves and just like see them all the time because they're around us constantly. We're just not able to see them. But it's weird to think that, like, if our eyes were able to pick up on different frequencies, we might see a whole bunch of other electromagnetic waves just flying around us all the time. Crazy. All right, cool. Lastly, let's go ahead and just do a quick check for understanding. So we have two different waves here, one from flashlight A and one from flashlight B, assuming that these both represent light waves. So first question for you is, which flashlight is brighter, flashlight A or flashlight B? Now, brightness of a light wave is reflected in the amplitude or the height of that wave. So I see that flashlight B has a higher amplitude because it's taller, therefore flashlight B must be the brighter flashlight. Second, one flashlight emits red light, one emits green light. Which one is which? Now, red light has a lower frequency and a longer wavelength than green light does, because red is at the lowest end and then up to blue is the highest frequency, shortest wavelength. So that tells me then that flashlight A must be my red light because it has a longer wavelength and a lower frequency than flashlight B. So flashlight A is my red light, flashlight B is my green light, and that is all I have for you. Thank you so much. Have fun getting to know your new wave friends. Love you.